In our previous section, we were looking at possible limits of sequences, and we were just making a conjecture because our sequences are not continuous functions, so we couldn't use the previous theorems we had from Calculus 1. However, in 10.2, we start out with this wonderful theorem, limits of sequences from limits of functions. And this theorem says that if you define a function to be equal to your sequence, and if that function has a limit, then the sequence will have the limit and it'll be the same. So what that means is we no longer have to make a table of values and make a conjecture. All we have to do is define our function. If we look at example 1, we have this sequence. And let's say our function, I'm just going to use n instead of x to be consistent with my sequence. Let's say my function is 3n to the fourth over n to the fourth minus 7. Then I can go ahead and evaluate that limit. As the limit n goes to infinity of this new function that I defined. So again, we can now treat sequences as if they were functions. The advantage is that all our formulas for sequences, or for limits, they still apply. So first note that as n goes to infinity, I get infinity over infinity. So I have a choice. I can do L'Hopital's with this limit, or what I'm going to do is simply divide everything by n to the fourth. So algebraically, if I divide all the terms by n to the fourth, I get 3 over 1 minus 7 over n to the fourth. And now you can see as n goes to infinity, this fraction in the denominator is going to go to 0. And this limit is simply equal to 3. So the limit of the sequence is 3. Notice in example B, we don't have the indices. So remember, if they're not written, you can assume we start with 1 and we end at infinity. So I'm going to define this function, f of n, and the roosters are in full range today. Now this is going to be n minus 1 over n to the power of n. Now notice when I take the limit, as n goes to infinity, I'm going to have a problem. But this is going to be infinity over infinity to the infinity power. I don't even know what that is. It's a bunch of indeterminate forms. So what I'm going to do inside the parentheses is I'm going to go ahead and divide by n, split it up. So it's 1 minus 1 over n to the n power. Now that's 1 to the infinity, still an indeterminate form. Remember, 1 to the infinity is not 1. We had a strategy for evaluating these by taking it e to the ln. And what that allows us to do is use the natural log to bring the exponent in the front. So this is simply the limit as n goes to infinity of e to the n times the natural log of 1 minus 1 over n. And now remember, since the exponential function is continuous, we're allowed to take this e and bring the limit up into the exponent. Off to the side, I'm going to evaluate this limit. So let me do that off to the side. My limit as n goes to infinity of n times natural log of 1 minus 1 over n. That's infinity times 0, which is an indeterminate form. I'm going to create a fraction by dropping the n below. I'll have natural log of 1 minus 1 over n in the numerator and 1 over n in the denominator. And now this is 0 over 0, which allows me to use L'Hopital's. So if I take the derivative on the top and the derivative on the bottom, this is going to be the limit as n goes to infinity. So the derivative of natural log of 1 minus 1 over n is 1 over 1 minus 1 over n. And then I'm going to times this by the derivative with respect to my variable n of 1 minus 1 over n. So I have to use a chain rule. Now I'm actually not going to compute that derivative because what I see is my shortcut. Notice when I take the derivative of 1, that's just simply 0. And then the derivative with respect to n of negative 1 over n, and look at the denominator, the derivative with respect to n of positive 1 over n, that's going to be the same. They'll just differ by a negative. So I'm just going to pull the negative out. And these guys are going to cancel because they're the same. So I don't even have to compute the derivative, but you can. So this is going to be negative limit as n goes to infinity of 1 over 1 minus 1 over n. And then since n is going to infinity, this fraction is just going to go to 0. And I'll have this whole thing is equal to negative 1. So let's bring this back. To be e to the negative 1, or simply 1 over e. So you still have to remember all those rules that we had when we computed limits in previous sections. Let's move on to some more examples. If I look at the natural log of sine of 1 over n, and I have my function f of n equal to the natural log of sine of 1 over n. Notice the natural log is continuous, sine is continuous. I can bring all these limits in. I'm not even going to write the limit. I just want you to notice as n goes to infinity, this 1 over n is approaching 0. Okay, so I'm looking at the argument of my sine function, which would mean that sine of 1 over n is approaching 0. But natural log of 0, it's not defined. So we have to think about this. If n is approaching positive infinity, then 1 over n is approaching 0 from the positive side. So it's getting closer and closer to 0 with positive numbers. In turn, that means that sine of 1 over n is approaching 0 from the right, or with positive values. So that means that this limit, as n goes to infinity, of natural log of sine of 1 over n is equal to natural log of 0, but we're coming in from the right and the natural log function as we approach 0 from the right is equal to negative infinity. So you could check this by making a table of values. You can also check this by graphing, and you'll see that this is going to diverge. Right, so the limit is negative infinity, and natural log of sine of 1 over n diverges. So you have to be a little bit creative sometimes. Or you could simply make a table of values. Let's do our last example, and then we'll look at some properties. So here we have our sequence. Now remember, if this set notation is not written, we can assume that it's there. And we can assume we're starting with 1 going to infinity if it's not written. If I take the limit as n goes to infinity of 2n over 7 to the n plus 2 over n, and here I'm assuming that my function is 2 to the n over 7 to the n plus 2 to the n. So as n goes to infinity, this is going to be 2 to the infinity is infinity, and then in the denominator I get infinity plus infinity, which is infinity. I get an indeterminate form. I don't want to do L'Hopital's because notice that involves, when I take the derivative, it involves logs. So instead what I notice is that I have a 2 to the n in the numerator and denominator. So algebraically what I can do is simply divide everything by 2 to the n to get 1 over 7 to the n over 2 to the n plus 1. And now it gets a little bit tricky. A lot of people say, oh, this is a fraction in the denominator, where the exponent is going to infinity. So it's just going to be equal to 0, but that's not true, because 7 over 2 is greater than 1. So as n goes to infinity, 7 over 2 to the n is also going to go to infinity. So this is the case of 1 over infinity. This is the case that this whole thing is getting closer and closer and closer. This whole thing is getting closer and closer to 0, which is what our limit is. So this sequence converges, if I have to state whether it converges or diverges, so it converges to 0. So we can use these properties if need be. Let's just say that we have two sequences, a sub n and b sub n, and they have limits a and b respectively. Then if you're going to take the limit and you're going to add or subtract these two sequences, since they have limits, you can simply add or subtract their limits. And these are similar to properties we had with limits when we're looking at real valued functions. So if you take the limit and you're just multiplying a constant by your sequence, you can just take the constant times the limit. If you're taking the limit and you're multiplying these two sequences, you can simply multiply their limits. And then the last property says that if you're taking the limit and you're dividing the two sequences, you would divide their limits. You just have to make sure that you don't get 0 in the denominator. So in this next box, what we're going to do is we're going to look at some terminology. A sequence is increasing if the terms get larger. So a sub n plus 1 larger than the term before a sub n. Example may be 1, 2, 3, and so on. So notice that as the terms go on, they get larger. That's not the same as saying non-decreasing. The difference between these two is non-decreasing says the terms can get larger, but they can also equal. An example of maybe a non-decreasing would be 1 comma 1, right? Not strictly getting larger, staying the same. 2 comma 2, 3 comma 3, and so on. Decreasing if the terms get smaller. So for example, 1, 1/2, 1/3, 1/4. This would be a decreasing sequence. Non-increasing, similar to decreasing, except for the terms can be equal. So we could have 1, 1, 1, 1. And that's actually a non-increasing because we're allowed to have the terms be equal, or we could throw in some halves, some thirds, some fourths. A sequence is monotonic if it's either non-decreasing or non-increasing. So sometimes it's nice to know if our sequences are bounded. So they're bounded above if you can find some number so that all the terms are less than or equal to that number. If we look at the sequence that I had written earlier for the decreasing, the 1, 1/2, 1/3, so on. Notice that if m is equal to 1, all the terms are going to be equal to 1 or smaller than 1. Bounded below is if there's a number n, so that all the terms are greater than or equal to that number. So if we look at the very first sequence, 1, 2, 3, and so on, notice that if n is equal to 1, then all my terms are equal to 1 or greater than 1. So we simply say a sequence is bounded if it's bounded above and below. So it has to be bounded both above and below. We're going to look at a special sequence, and this is going to come up a lot. It's called a geometric sequence. A geometric sequence is where each term is obtained by multiplying the previous term by a fixed constant that we call r. R stands for the ratio. If we look at this example 3 to the n, and we look at that sequence, that's 3 to the 1, 3 squared, 3 to the third, 3 to the fourth, and so on. So you notice to get from one term to the next, you're multiplying by 3. So in this case, our ratio r is equal to 3. Now if we have a geometric sequence, then we can tell if it converges or if it diverges. So let's say we do have this ratio of a geometric sequence. We have our r value. If we take the limit of our sequence and it's equal to 0, or it will be equal to 0, if the absolute value of r is less than 1. If r is equal to 1, then the limit is 1. If r is less than or equal to -1 or greater than 1, then the limit does not exist. If our ratio is positive, then our sequence is either going to be monotonic, or it is a monotonic sequence. If r is negative, then we say that the sequence oscillates. So that would be where you see the terms go from negative to positive, negative to positive. And that's what we call oscillating. We're going to determine if these sequences converge or diverge, and then we're going to discuss the behavior. In example A, again, we're assuming we're starting with 1. R is equal to negative 0.2. So since the absolute value of R is less than 1, I don't have to take the limit. By this theorem, I know that it's going to converge to 0. So this sequence converges to 0. And its behavior? Well, since R is negative, then it converges by oscillation. So I can just add here by oscillation. In example B, I see that R is equal to 5 over 4. And since R is greater than 1, I know that this sequence diverges. And since it's positive, then it's monotonic. So I could say it diverges monotonically. Oops. Let's put all these limits together. In example 3, I want to determine the limit of this sequence. And notice it as the limit as n goes to infinity of 2n squared plus n over 3n times 5n squared minus 1. That's going to be infinity over infinity, which is an indeterminate form. So I'm going to use a bunch of stuff. I'm going to break this up into the limit as n goes to infinity, because it seems like a big, huge mess, of 1 over 3 to the n times the limit, which I'm allowed to do, as n goes to infinity of 2n squared plus n over 5n squared minus 1. So I'm doing that because 3 to the n is an exponential function, whereas 2n squared plus n over 5n squared minus 1, those are polynomials. So they're a little bit different. If we look at this first limit, this is going to be a geometric sequence. This is the limit as n goes to infinity of 1/3 to the n, which is geometric. Where r is less than 1, so it's going to be 0. And then this next piece, I can go ahead and divide everything by n squared to get the limit as n goes to infinity of 2 plus 1 over n over 5 minus 1 over n squared. And now the limit is n goes to infinity, 1 over n goes to 0. 1 over n squared also goes to 0. The first limit, r is equal to 1/3. It's geometric. So in this case, the limit is going to be 0 times 2/5. So 0 times 2/5 is simply 0. Something that I would like to talk about is a factorial. These are going to come up quite a bit in later sections. So first of all, a factorial, and we use the exclamation point, is simply a product where we keep reducing by 1 until we get to the factor 1. So for example, 5 factorial says we start at 5 times 4 times 3 times 2 times 1, which is 120. And when we talk about factorials, we can assume that 0 factorial is simply equal to 1. I just wanted to make sure we all knew what a factorial was before we go on to some more theorems. A theorem that came up when we did limits for Calculus 1 was this idea of a squeeze theorem. It also applies for sequences. So let's just say that we have 3 sequences where one is always between the other two for some index n. So if we take the limits of the outer sequences and they're equal to some limit L, then that squeezes or forces the middle sequence to also have a limit of L. Let's look at example 4. Notice that if I were to take the limit, oops, let me erase that. If I were to take the limit as n goes to infinity of cosine of n over e to the n, well, the denominator is going to be infinity, but I don't know what the numerator is because the cosine function oscillates from -1 to +1, -1 to +1, right? And values in between. So what we're going to do is we're going to build up and we're going to use this squeeze theorem. So let's go back to our trig. We know that the cosine is between +1 and -1. So now I simply have to build up to my expression cosine of n over e to the n. I'm going to divide each one of these terms by e to the n. I do have to be careful because these are inequalities. I have to make sure that these values that I'm dividing by are not negative, because if they are, then I'm going to have to flip the sign. But e to the n is always positive. And in fact, since n is going to positive infinity, it's going to be e to some positive exponent, which is positive. So now I simply have to take the limit for all 3 pieces as n goes to infinity. So the limit as n goes to infinity of -1 over e to the n less than or equal to the limit as n goes to infinity of cosine of n over e to the n less than or equal to the limit as n goes to infinity of 1 over e to the n. Looking at these end functions, the limit as n goes to infinity of -1 over e to the n is -1 over infinity, which is simply 0. So that's less than or equal to the limit as n goes to infinity of cosine of n over e to the n, which is less than or equal to the limit as n goes to infinity of 1 over e to the n. That's also 0. So notice that the limit as n goes to infinity of cosine of n over e to the n has to be equal to 0 by the squeeze theorem. So I need to make, and this is how you would show your work. You wouldn't skip these steps. So I need to make my conclusion. My conclusion is, I'll use some conclusion word like thus. The limit as n goes to infinity of cosine of n over e to the n is equal to 0. Why? By the squeeze theorem. That would be the justification. moving on. Some theorems that may be helpful for you is this bounded monotonic sequence. So if we do have a monotonic sequence that is bounded, then it's going to converge. You don't have to do any computations. You don't have to take the limit. So that's a nice little trick. Something else that comes up is growth rates. And this is referring back to previous sections and in calculus when we talked about growth rates as well. So if you do take the limit of a division of two sequences and it's equal to 0, that just tells you that the bottom is growing faster than the top. So in your e-text, they'll say that the top sequence appears before the bottom sequence in this list of common sequences that grow at a certain rate. So natural log of q of n grows slower than n to the power of p. So we can use these growth rates. In example 5, we want to determine which sequence has the greatest growth rate as n goes to infinity. So I can simply take the limit as n goes to infinity, and it really doesn't matter which one you put on top. I'm going to just put them as I'm reading them. Natural log of n to the 4th over n to the 1/3. And notice as n goes to infinity, natural log of infinity is infinity. So this is going to be infinity over infinity to the 1/3 is still infinity. So I could use L'Hopital, or I can also notice that in my numerator, I can bring the exponent 4 out in front of the natural log. So it's the natural log of n over n to the 1/3. And the natural log of n as n goes to infinity is infinity over n to the 1/3 is infinity. So again, I can use L'Hopital's, or I can use that theorem. So in that theorem, natural log grows slower. I'm looking at these first two entries. Since the natural log grows slower, then this is going to be equal to the 4 stays times 0. So you can use this growth theorem to evaluate limits, and then my conclusion would be that b sub n grows faster. By the growth rates theorem. Something else you can also use, even though it's not in the theorem, is that if you take the limit as n goes to infinity and you get infinity, then that means the top one grows faster. So you can also use the limit of infinity. So if I was going to find the limit in example 6a, I would get the limit as n goes to infinity of n factorial over 5 to the n. So as n goes to infinity, I get infinity over infinity indeterminate form. I could use L'Hopital's, but I have a problem. I don't know how to take the derivative of a factorial. We don't have that yet. So I'm kind of stuck. I'm stuck with maybe using the growth rates theorem. From that theorem, I know that n factorial grows faster than the denominator 5 to the n. So if you just look back at that chart, it says b to the n grows slower than n factorial. So that's the form that we have. And since I know that, then I can say that the limit as n goes to infinity of n factorial over 5 to the n, I could say that that's equal to positive infinity. Let's look at another example. If I were to evaluate this limit as n goes to infinity, I have n to the 10 natural log of n over n to the 12. And again, I have a problem because I get the indeterminate form infinity over infinity. I could use L'Hopital's. I can't use growth rates just yet because there's 3 separate functions. However, I could use some algebra to rewrite this as natural log of n over n squared. So I'd still get infinity over infinity, and I can use L'Hopital's, or I could simply use the growth rate theorem to note that n squared grows faster than natural log. Natural log actually grows the slowest out of all these. So this limit as n goes to infinity of natural log of n over n squared is going to be equal to 0. The last thing we want to look at is we want to look at the formal definition of a limit of a sequence. And this goes back to calculus when we looked at the formal definition of a limit. It's very similar. So a sequence converges to some limit, provided these terms can get arbitrarily close to our limit. Precisely, the sequence has a unique limit L if we can find some epsilon greater than 0 and a positive integer n, so you could think of this n as being a number that you can bound your terms by, such that the absolute value of a sub n minus L is less than epsilon whenever your indice n is greater than the number n that we find. If we can find this capital N, then we say the limit converges to L, and we write the limit as n goes to infinity of a sub n is equal to L. If it does not converge, it will diverge. So we're going to go through the proof in example 7 that the limit as n goes to infinity of 1 over n is equal to 0. So here note that my a sub n, always forget that. My a sub n is 1 over n. Since this limit is equal to 0, my L is 0. So the first part of our proof is to find for any epsilon that capital N. So this is scratch work. This is actually not the proof. So let's just assume that we have some epsilon greater than 0. And our sequence a sub n is equal to 1 over n. So we're supposed to look at a sub n minus L being less than epsilon. We know our L. Our L is 0. And we know our a sub n. That's 1 over n minus 0. So this is where I'm at. I need to find this capital N. I have the absolute value of 1 over n is less than epsilon. And I don't need the absolute values because remember our limit is as n goes to infinity. N is not going to be negative. So I can drop them. And I want to solve for n. So remember in algebra, if you have two fractions and an inequality, you can flip them, but you have to flip the sign. So n is greater than 1 over epsilon. What I'm going to do is I'm going to let my capital N be equal to 1 over epsilon. So the whole point of this scratch work was finding this capital N. This is not the proof. It's just scratch work. So here's my proof. Let's assume, suppose, let is the shortest word. So let's let epsilon be greater than 0. And I'm going to assume that my indices n are all greater than capital N, this capital N I found, where n is equal to 1 over epsilon. Then, and now I just have to show that a sub n minus L is less than epsilon. So I'm going to start with what I have. I know that n is greater than capital N, and I know capital N is 1 over epsilon. So I know that's true. And this part of the proof, you're pretty much just working backwards from your scratch work. So I have 1 over n is less than epsilon, which is 1 over n in absolute values less than epsilon. That's still true. 1 over n minus 0 is less than epsilon. And I'm done. I've shown that for this particular capital N value of 1 over epsilon, I get a sub n minus L is less than epsilon, which is what I was supposed to show. Therefore, I can conclude that the limit as n goes to infinity of 1 over n is equal to 0. And oftentimes when we end a proof, we'll use the Latin abbreviation QED for Curat Demonstratum. Oh God, I can't speak Latin very well. Anyway, I've shown what I need to show. And that's it for this section.